All right, in this video, we are going to do section 5.2, the definite integral. So we are going to take all the information that we learned in the last section in 5.1, and we're going to convert it into what the idea we're going to use going forward after this section. So a lot of the stuff in this section is going to look very familiar from the last video, but we're going to kind of define things in a little bit different way. All right, so if you remember the formula we did last time, when we wanted to calculate the area under a curve, we used the limit definition, the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. And we went through the process. What I can finally say now is that what the idea was that you were calculating was the idea of a Riemann sum. So a Riemann sum is this funny limit summation formula right here. What we want to be able to do is, while this is not the best way to do it, what eventually we want to do is to develop this into the idea of a definite integral. The definite integral is the backbone to almost everything that we do in this class. Every single topic involves a definite integral of some type. So you can read through this pink box if you'd like to. It's a lot of the same stuff we already talked about last time, but essentially the big thing to note here, and like I said, if you need to pause the video to write anything down, the big thing here is this conversion right here, is that this Riemann sum that we talked about in the last video is now going to be defined as a definite integral of f from a to b. So when we see this integral symbol pop up in this class, this is how I'm going to usually say it. I will usually say this is the integral from a to b. So the integral will have a lower parameter and an upper parameter given. And then we're just going to call it f of x dx. The reason this is the more formal way of doing it going forward is because you don't have to worry about the funny x sub I or the delta x all the time. It's a more direct way to find an integral or find the area under a function. So the Riemann sum, or the limit definition we talked about last time, is equivalent to the integral from a to b of f of x dx. So the idea, like I said, a lot of the first stuff we're going to see today is pretty much exactly the same. So if you remember from the last video, when we did these limit definitions, we had two parts that were necessary. We had to be able to find delta x, which was b minus a over n, and we had to also be able to find x sub I, which was defined as a plus I delta x. Our job now is going to be is if I give you the Riemann sum definition of the area, can you convert it into its integral representation? So I'm going to leave these formulas up here at the top of your screen, and here's going to be our first of two examples here. I want you to take this limit, and it's really ugly, and let's make it look a little bit nicer. So we have the limit as n approaches infinity of the summation from I equals 1 to n of e raised to the 2 plus 5i over n over 1 plus 2 plus 5i over n, all of that multiplied by 5 over n. We saw a conversion like this in the last video, and if you remember, this whole thing right here is your f of x sub I, and this part here on the end is your delta x. From these two bits of information, you're going to need to figure out what is your a, what is your b, and what is your f of x function. And like I told y'all in the last video, the easiest thing to find here is your f of x first. Because all you need to do is take the f of x sub I function and replace those ugly x sub I terms with just x. So that would be e to the x over 1 plus x. And that's going to be the function that we plug into our integral. You also need your a and b value in order to write the integral. Now, the good thing about your x sub I is that the number that's being isolated is your a term. So since we have a 2 that is isolated in both of those terms, we can say that our a value is 2. Delta x, the top of your delta x function has to be b minus a. And since I know a is 2, all you have to do is ask yourself, what number minus 2 is going to give me that 5 on top. So in this case, that would be 7. And if you take these 3 bits of information and plug them into the definition of an integral, I can say that this Riemann sum is equivalent to the integral from 2 to 7 of e to the x over 1 plus x dx. That is your answer. And this is what we're going to work with a lot more going forward. I'm going to show y'all one of the limit problems a little bit later, but in the end, we would rather work with the integral symbol versus the limit definition. Kind of like in Cal 1, you'd rather know the shortcuts for derivatives versus doing the limit definition of the derivative. Let me do a second one, just so you have it in your notes. Can you express the following Riemann sum as a definite integral? So we have the limit as n approaches infinity of the summation from I equals 1 to n of 1 over 1 plus I over n squared, all times 1 over n. So remember, this is what you're matching up to as the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. So just like the last problem, if this whole piece right here is your f of x sub I, then it's very clear if you were to replace your x sub I with just x, we could say that f of x is just equal to 1 over 1 plus x squared. Just replace that I over n with x. Now you've got to make sure you can find your a and your b. So remember that a is just the number that's being added to your x sub I term. But since there's not a number being added to the I over n, it is understood that your a value is 0. And then to calculate your b value, you look over here at your delta x. Since that 1 comes from the subtraction of b minus a, and you know that a is 0, you have to ask yourself what minus 0 gives you 1, and that's very obviously going to be 1. You take those 3 bits of information and you can convert them into the integral representation of this limit. And that would be the integral from 0 to 1, so that's a to b. You take your function, which is 1 over 1 plus x squared, and then you put dx. This is the integral representation of that Riemann sum. And that's what we're going to be working with pretty much non-stop going forward after I show y'all one long limit definition. So that being said, let's go the other direction now. This is what we did last time, but I want to make sure everybody gets the connection. Instead of me giving you a function and an interval and saying find the Riemann sum, let's make sure that you can go from an integral to a Riemann sum. So if you have the integral from 2 to 5 of x squared plus 1 over x dx, I want you to do 3 things. I want you to find delta x, I want you to find x sub I, and then rewrite your integral. And once again, just like last time, do not evaluate this yet. We're going to start evaluating after this slide. All right, so remember, delta x can be found by doing b minus a over n, where a and b are just the parameters of your integral. So that would be 5 minus 2 over n, which is 3 over n. So we got that part done. X sub I has the formula a plus I delta x. So in this case, a is 2, and you're going to multiply I by the delta x term you just found, which would make this 3i over n. Then you're going to take these 2 bits of information and you're going to plug this into your limit definition. So this would be the limit as n goes to infinity of the summation from I equals 1 to n. So you're going to replace both of these x's with your x sub I terms. So that would be 2 plus 3i over n squared plus 1 over 2 plus 3i over n. So that is your f of x sub I term. And then you multiply all of this by your delta x, which is 3 over n. And this is your Riemann sum definition of the integral that was given. Now, what we're about to look at on just a second is that now that we have things like this, the question is, we have still not found the exact area under a curve. We learned how to write it and how to express it, but the question is, how do you evaluate something like this? Before we do one like that, there's a couple of expressions that we need to go over. And we've got 4 of them, right? So when we start working out these summation problems, is that there's going to be some values that pop up that we're going to need to know representations of. Now, we're not going to go through the formal idea of where these come from. That's beyond the scope of this class. But we are going to give them to you. So please, if you need to, pause the video and write these down, because any of these 4 could pop up. But I'm going to read through them before I go on to the problem. So at any point, you run into a summation of just the number 1. We can express that as just an n, because the goal is going to be in just a minute is to get rid of all of the summations. You can't evaluate summation problems as they sit. If you can write something as just the summation of I, we can express that as n times n plus 1 over 2. If you get a summation of I squared, it would be n times n plus 1 times 2n plus 1 over 6. And finally, probably won't happen very often, but I did go ahead and put it on here just in case. If you happen to get an I cubed term, it would be all in brackets, n times n plus 1 all over 2, and then you have to square it. This one right here is probably pretty rare for what I'm going to make y'all do, but please jot it down just in case. The other 3, I think, all pop up in the problem I'm about to do. So since this is this is a very tedious problem, we're only going to do one of these, because in the next video, we're going to learn the shortcuts. It's kind of like in Cal 1, if you took Cal 1 here at Mississippi State. We make y'all do the limit definition of a derivative, and then we teach y'all the shortcuts after that. It's the same thing here. I need to formally show you the actual way that integrals are evaluated before I just give you the shortcuts. So I want you to work out using the limit definition of the integral to evaluate the integral from 1 to 5 of 3x squared plus 7x. So what you're going to have to do is convert this into a Riemann sum, and then we're going to have to do a bunch of algebra. Before we can turn this into a Riemann sum, we need 2 things. Number 1, we need delta x. So that is b minus a over n, which would be 5 minus 1 over n, which is 4 over n. Remember, the a and the b come from the integral. And then you also need x sub I, which is a plus I delta x, which would end up being 1 plus 4i over n. Taking those 2 bits of information, let's convert them in, let's rewrite our area formula. So this would be equal to the limit as n goes to infinity of the summation from I equals 1 to n. I'm going to take my original function and I'm going to replace those x's with x sub I. So it would be 1 plus 4i over n squared plus 7 times 1 plus 4i over n. And all of that is multiplied by delta x, which is 4 over n. And up until this point, we have just stopped here. For the first time now, we're going to actually work this all the way out. So get ready for a lot of algebra here. Because your job here now is to take all of this and you need to put it all together as common terms. So you need to expand all of that. So this will end up being the limit as n goes to infinity of the summation from I equals 1 to n. So inside of my bracket, first thing I'm going to do is I'm going to FOIL 1 plus 4i over n by itself. So y'all should all know how to FOIL. So if I FOIL this, it should be 1 plus 8i over n plus 16i squared over n squared plus 7 times 1 plus 4i over n, all of that times 4 over n. All right. Inside the brackets, I'm going to multiply all three of these terms by 3. I'm going to multiply both of these terms by 7, and I'm going to put them all together. So you should end up with the limit as n goes to infinity of the summation from I equals 1 to n. All right, so inside your brackets, 3 times 1 is 3, and 7 times 1 is 7. So 3 plus 7 gives me a constant of 10. Your I terms, 3 times 8 is 24, 7 times 4 is 28, so 28 and 24 is going to be 52, so it's plus 52i over n, and then you only have one I squared term, so 3 times 16 would be plus 48i squared over n squared, but keep in mind, this is all still need to be multiplied by 4 over n. Now you're going to take the 4 over n and distribute it to all three of those terms. So this would be the limit as n goes to infinity of the summation from I equals 1 to n of, that would be 40 over n plus 208i over n squared plus 192i squared over n cubed. All right, so you've expanded. That's job number 1. We got it expanded. Now you're going to have to write this as 3 separate limit problems or summation problems, because in the end, the only thing that the summation applies to is your I terms. So here's what we're going to do. We are going to rewrite this as the limit as n goes to infinity. So that part doesn't matter. I'm going to apply the summation to all three of these, but everything that doesn't have to do with an I term, I'm going to actually factor it out front. So for example, this 40 over n, if I were to factor the 40 over n out of the first summation, that would leave me with a 1 left over. Plus, if I factor the 208 over n squared out of the second one, that would leave a summation of just I. And then same thing on the third one. If I factor out the 192, oops, not the I, I'll leave the I inside, I'll leave that. The 192 over n cubed inside my last summation, that leaves an I squared. This is where I suggested y'all write those formulas down, because on the previous slide, we now have a formula for all three of these, that you can now get rid of all three of these summations. So what I'm going to do is I'm going to plug in those values. This would be the limit as n goes to infinity of, you'll have 40 over n times. The summation of just the number 1 is n, plus 208 divided by n squared. The summation of I is n times n plus 1 over 2. Right? And then plus 192 over n cubed. The summation of I squared is n times n plus 1 times 2n plus 1 all over 6. All right, so now we got to clean all of this up. So it's not going to simplify perfectly, but we're going to simplify it the best we can. The only thing that I'm going to do first is I'm going to simplify a few things here just to make it a little bit easier. So for example, like n over n cancels. I'm going to go ahead and take care of that. 208 divided by 2 is going to give me a 104. Excuse me. And then let's see, 192 over 6 is going to end up being, let's see, 32. Yep, so make sure. So at least it makes a little bit. Everything else I need to expand, and then we'll see if anything else can be canceled. So this is the limit as n goes to infinity. So you just have a 40 plus 104 over n squared multiplied by, if I multiply the n times n plus 1, that's n squared plus n plus 32 over n cubed, all of that multiplied by, if you were to expand all of this, so let's see, this right here would be n squared plus n, and get rid of that. And then if I FOIL that, it would be 2n cubed plus 3n squared plus n. I'm doing a little mental math here, but y'all should be able to FOIL all that together. All right. And then if I multiply what I can together, you end up with the limit as n goes to infinity of 40 plus 104 n squared plus 104 n over n squared plus, let's see, 64 n cubed plus 96 n squared plus 32 n all over n cubed. Here's where this is why you covered limits in such detail in Cal 1. Now you want to apply your infinite limit definitions to all three of these terms. So when you apply the infinite limit to all three of these, let's see what you get. There are no n's in the first term. So in that case, nothing happens and you just get a 40. If you remember back in Cal 1, when you do infinite limits where the highest power on top and bottom are the same thing, you do the ratio of coefficients. So since you have a 104 over a 1, you just get 104. And it's actually the exact same on the last one. There's an n cubed on top and bottom, so that ends up just giving you 64. And then you can add all of these together to give you a final answer of 208. So the exact area under the curve of from 1 to 5 of 3x squared plus 7x is going to be exactly 208 units. Now, as you can tell, that's a very tedious process. And if you need to pause the video and kind of rewind and rehear stuff, that's fine. You're not going to have to do many of these. There's a couple of them on your homework, but kind of like in Cal 1. In the next video, we're going to learn a shorter way to do this, but you may be tested on the long definition way of evaluating an integral. So make sure you understand the process. And the biggest thing is to memorize these summation formulas that are going to pop up about halfway through. But that's the only one that we're going to work during this video. What the rest of this section is all devoted to is now that we're going to move into all integrals, we need to know some properties of integrals, kind of like you had properties of limits and derivatives. So I'm going to let you read through these properties. I'm going to read through them kind of quickly, but like I said, with this being a video, you can pause it at any point and let you write them down before continuing. But let me kind of read through these properties 1 through 5. Property 1 says, if you integrate from a to b of a constant dx, your answer will just be c times b minus a. All right, kind of like limits and derivatives worked. When you're doing addition, and this also applies to subtraction that you can see on number 4, you can actually integrate two functions separately and then put them together with addition or subtraction. It's not that common, but it is a property that we can use. And then just like in derivatives, if you have number 3, if you have a constant that's multiplied by a function inside the integral, then you can factor that constant out front and then you can just integrate the function and multiply your final answer by the constant. Property number 5 has its own little box down at the bottom because it's a little bit different. What it essentially says is, how do you put two integrals together that don't have the same parameters? So what this says is that if you have an integral from a to c and an integral from c to b, as long as the upper parameter of the first and the lower parameter of the second integral are the same thing, you can put these together and the a and the b become your new parameters of the final integral. But if the upper of the first and the lower of the second don't match, you cannot do this. Now, while these next two properties are not numbered, they are actually very important, so I kind of stuck them up here in blue boxes. A couple of properties that we're going to see pop up throughout are the following. If you're integrating from b to a, so let's say that your parameters are backwards and your bigger number is the lower parameter and your smaller number is the upper parameter, you can flip-flop these as long as you pull a negative out front. So the integral from b to a is the same thing as the negative integral from a to b. So we'll use that property a lot in this class. And then, not as common but still popular, if the upper and the lower parameter are the exact same number, you don't need to do any work. Your final answer will always come out to be 0, because if the upper and lower parameter are the same, that means your delta x is going to end up being a width of 0, and multiplying a bunch of rectangles by 0 is not going to give you an area. So use that when it pops up. All right. So let's move back and let's do something besides rectangles. Let's do some integrals. Remember, integral is just area under a curve. Let's see if we can do something like this. The graph of G on the right consists of two straight lines and a semicircle. Evaluate each integral by interpreting it in terms of area. So we're going to use a little bit of geometry here to help us. So I'm going to try to color coordinate the best I can here. So part A, the integral from 0 to 1. All right, the integral from 0 to 1 is going to be this part. So we only want to end up doing the part in purple. I'll put a little purple dash over here so you can color coordinate. So as you can tell, if you look at that purple shaded figure, you have two things. You have this rectangle right here. So that rectangle has a base of 1 and a height of 2. So if I take the area of the rectangle, so that is this part right here, a little darker there, I'm going to add to this the area of that triangle, which we know triangles have a formula of 1/2 the base. So the base of that triangle is 1, and the height of that triangle is 2. So all I'm doing here is I'm taking the area of my rectangle and I'm adding the area of that triangle to get the total area under the curve. And if I were to work this out, this would be 2 plus 1, which comes out to be 3. That is the area between 0 and 1. And that's all an integral is doing, is you're finding the area under the curve. All right, let me change to red. What about the area from 2 to 6? So 2 to 6 is going to be this whole part down here. Now, for the first time, we have an area, remember, because you're trying to find area under a curve. But since the curve is below the axis, any shape that's below the x-axis is actually going to represent a negative value. I know it's technically area, but area under a curve that's already below the curve has to be represented as a negative value. So in the end, I know it's going to end up being negative. Other than that, you need to calculate the area of this semicircle, all right? So the area of the semicircle would be, so circle is pi r squared, so a semicircle would be 1/2 pi times the radius squared. And the radius of this semicircle is 2 units. So 2 squared is 4, and half of 4 is 2. So that should simplify into negative 2 pi units. And remember, it's only negative because that area is below the x-axis. All right. And finally, what if you want to find the area of the whole thing? So say that for the end. We'll do this in blue. All right. So in blue here, you want to find all of this area. So you're going to have this triangle, this semicircle, which is negative, and this little bitty triangle that you have to put together. Now, the good news is that we've already found the area of this semicircle. So I can go ahead and call that negative 2 pi. I'm going to add to this the area of this first triangle, which would be 1/2 times base. So the big triangle has a base of 2, and it has a height of 4, plus the area of the smaller triangle, so this part right here, all right, this whole part over here is blue. That smaller triangle would be 1/2. The base and the height are both 1. Simplify that. This would be negative 2 pi plus 2 times 4 is 8, and half of 8 is 4, plus 1/2, which will give me an answer of negative 2 pi plus 9/2. And that is your final answer. If you did it a different way and you got an answer of like 9/2 minus 2 pi, so you flip-flop those two numbers, that's fine. This is just the way that I preferred to do it, but it's not wrong as long as the values are correct. But remember, all an integral is the area under a curve. So if you're able to put it into geometric representations, that makes it a lot easier. Now, not everything in this class is going to be geometric, which we're going to see going forward, but it's nice to kind of get that foundation built while we're here. Where it can be challenging is that, what if I want you to do the exact same thing, but I don't give you the picture, which means you have to draw the picture yourself. Now, that would be nice if it was one big picture, but what if I give you 2 separate functions and I want you to use the properties of integrals to help you? So what if we want to integrate from negative 4 to 4 of 2x minus the square root of 16 minus x squared? Remember, your properties of integrals say that just because it's being subtracted, what you can actually do here to make this a little bit easier is you can write this as 2 separate integrals. I'm going to integrate on the same parameter of just the 2x minus the integral of the same parameters of the square root function. All right, so what I'm going to do is I'm going to actually draw each of these pictures separately, and then we're going to calculate each area and put it together. So when it comes to the first graph, so 2x from negative 4 to 4. So 1, 2, 3, 4, 1, 2, 3, 4. If you plug negative 4 into 2x, you're going to end up down here at negative 8. And then if you plug 4 in, you're going to end up here at positive 8. And you're going to end up having a straight line from here to here that goes through the origin. Now, what's neat about this is that if you were to calculate both of these areas of these triangles, so the area of this triangle, which is below the x-axis, and the area of this triangle, which is above the x-axis, they're both the same area, but one we have to represent as negative and one we have to represent as positive. So since both of these areas cancel each other out, when it comes to integration, it's actually possible to get an area of 0. That may not seem like logical sense to everybody, but when it comes to area under a curve, since both areas are the same, but one's positive and one's negative, they cancel each other out. All right, so this first part is 0. What about this part? This may not be as common a shape to everybody, so let's see what ends up happening here. All right. If you were to plug negative 4 into this function, you would get 0. If you were to plug positive 4 into the function, you would also get 0. And then what I would probably also do is plug 0 in, because 0 is a pretty nice number, and you would get an answer of 4. So for those who didn't know what this shape was, a square root of a quadratic function actually draws a semicircle, and it looks something like this. Now, since this entire semicircle is above the x-axis, we are going to get a positive area here. So we can use geometry, and the area of a semicircle is 1/2 pi times the radius squared. And the radius here would be 4 units. So 4 squared is 16, and half of 16 is 8 pi. That would be the area of that second integral. But don't forget, your operation still has to come down in between them, which is a subtraction. So if I take my area of 0 and subtract my area of 8 pi, you actually get an overall area of negative 8 pi units. So that's how you can take a really ugly function, break it up into 2 separate integrals, do each geometric area separately, and put your final results together. While we don't always use properties for everything, sometimes it makes life a little bit easier if we understand them. So very good. All right, and then kind of wrapping up this video, a couple of easy problems to finish. Just so we can kind of get ready for the next section we're going to get into, just a couple of those properties that pop up. So what about that property 5 down at the bottom that I talked about, combining integrals with different parameters? So no numbers, no functions here. But what if I asked you to take the integral from -2 to 2 of a function, add to that the integral from 2 to 5 of the same function, but then take away the integral from -2 to -1 of the same function? So while you can do all of this in separate steps, here's how I usually represent this to students when I teach this. So take your first integral here. We want you to go from -2 to 2. So we're going to find the area under the curve between these two parameters. So that takes care of this one. Then I want you to add to this the integral from 2 to 5. So that means if you start at 2 and you go to 5, that means we now pick up this entire integral. So just adding those first two together would actually give us the integral from -2 to 5 of the same function. That's what property 5 says you can do. Here's the extra part of property 5. What if you need to subtract off a piece? So what about the integral from -2 to -1? So let's say -1's right here. I want you to take this piece off. So we're going to omit that part of the integral, which means we don't want to go from -2 to 5 anymore. You now only want to go from -1 to 5 of the function. So while sometimes breaking up the integrals like on the last problem is beneficial, when we get to problems like this going forward, it makes no sense to do 3 separate integrals here and then put all the answers together. On one like this, it may be beneficial to put them all back together, and then we could just solve one problem and be done. That's going to be the challenge in this class, is that knowing which way may be easier. Is it easier to keep it as one integral and work from that? Or is it easier to break it up and work it from there? We're going to go over all of those strategies throughout this class. All right, and last but not least, just to kind of do a couple more of those properties I showed you, what if I actually put numbers involved? If I tell you that the integral from 0 to 9 of a function is represented by 37, and the integral from 0 to 9 of a different function is represented by 16, and can you tell me what is the integral from 0 to 9 of 2 times the f function plus 3 times the g function? So this is another example where breaking it up is going to be the more beneficial way of doing this. So first thing I can do here is that since both of these functions are being added together, I can rewrite this as 2 separate integrals. I can do it as the integral from 0 to 9 of 2 times f of x dx plus the integral from 0 to 9 of 3 times g of x dx. So that's the first property you can do. Our new property here is that when you have a constant in front of your functions, you don't have to leave those inside the integral. You can, but sometimes it's easier if we can factor those out to the front. So I can actually rewrite this as 2 times the integral from 0 to 9 of f of x dx plus 3 times the integral from 0 to 9 of g of x dx. And now if you look above at the values, I gave you this value and I gave you this value. Now going forward, I'm going to make you find those values on your own. But at this point, once you find the integral values, you can plug them in. So this would be 2 times 37 plus 3 times 16, which comes out to be 74 plus 48, which adds up to be 122 units. So there's where you can, once again, that is where the properties of integrals come into play. Not every problem this semester will make us do these, but it's good to know them and get the foundation built now before we get into the more difficult stuff going forward. All right, so that ends the video for section 5.2. In the next video, now that we've covered the long way, the limit definition of how to do integrals, I'm going to show you all the shortcuts of how to do the integration. If you don't remember, the second video for this class was on antiderivatives and how you found antiderivatives. If you need to, you might want to go back and look over that video again, because in the next video, we're going to be using that antiderivative idea to help us develop shortcuts for integration. I will see you all in the next video.